The slab is 125 millimeters thick. Floor finishing is 2 kilonewton per millimeter square. Exterior infill walls are 1 brick, which is 0.25 meter thick. Interior infills are half a brick, 0.125 meter thick. Assume a 20% opening in infill. We can also ignore that, but just to get a better estimate of the loads, we can take it into account. Live load on the floor is 2.5 kilonewton millimeter square. Fy is 500 megapascal. Unit weight of RC is 25 kilonewton per meter cube, and that of masonry is 20 kilonewton per meter cube. Column size is constant at 600 by 600 millimeters up to 4th story, and remaining are 500 millimeters by 500 millimeters. Use EC8 spectrum or soil type B at 0.5 G level, concrete characteristic strength 30 megapascal. All right? So this is our grid. 6.5 meters bay, 4 of them together. 5.5 meters bay, 3 of them in the short direction. So I have a long direction and a short direction, right? So if you recall our steps, what should we do now? Our plan is 26 times 16.5, which is roughly 429 or 430 meters square. Our theta D is 2.8%, which is 0.028 radians. Right? Plastic rotation at life safety. Our maximum is 0.00 or 0.02. But let's say our ASC 41 gives us a value range, and it's 0.01875. That's our plastic rotation, which is theta PB. Following so far? Strain in steel is 500 divided by 200,000, which is 0.0025. Now, we have HB. Equals 0.5 times strain times LB over theta D minus theta PB. Got it? Short direction.
प्लास्टिक रोटेशन है नहीं ये है ना 0.017 ये वाला टिक मत
Okay, so let's start with long direction. HB, if you calculate using this equation, HB would be 0.878. Your HB over LB ratio is 0.135, which should be okay, right? Because you need your maximum is 0.14. Right? Now, you have to go through a little exercise, and maybe I'll just skip through it, but you can go through it in much more detail on your own. But Your dead load intensity of the slab comes out to be 5.125. That includes finishes as well, so your slab is 125 millimeters thick. Floor dead load is 5.125 times 429. Live load on the floor, again, we're assuming a 25% allocation of live load to seismic mass. So you have 2.5 times 25 times 429, which is 268. Total seismic weight in each floor, roughly 2467. Now, when you do a lumped mass model, half of the story mass goes on to bottom and top, right? So you have to find out the mass for each, because the column sizes are given, because infill is given, there are beams and slabs in different directions. So you'll use that to calculate your masses, right? So column up till 4th level, your length is 3.3 meters minus 0.85, which is your average beam depth, right? We just found that out from here. That's your length. Breadth is 0.6 by 0.6. Column above 4th level, same height, 0.5 by 0.5 cross section. Your quantity is 20, because if you count the number of junctions here, 1, 2, 3, 4, 5 times 4 is 20. Following so far? Maybe or maybe not. Just calculating the seismic weight right now. Beam in short direction. And you can do the same exercise in short direction and get, which is done somewhere down here. You can get the cross section for the short direction beam. So if you do the same exercise for short direction, you'll get, I might not have done it, but if you can just calculate the beam HB in short direction, you'll get 0.75, and your HB to LB ratio is satisfying. So you can use that over here. You count the number of beams in long direction and short direction. So long direction 1, 2, 3, 4. 4 times 4 is 16. Short direction 1, 2, 3. 3 times 5 is 15. So 16 and 15 respectively. The unit weight of concrete is 25. The weight of that element, beam and column, is right here. Okay? So volume times the unit weight. Then you do your exterior infill and your interior infill, which is of masonry. So your unit weight is 20. Your length is 85. Exterior infill length is 85. How do you calculate that? Your perimeter. Your interior infill length is 101.5. How do we calculate that? 1, 2, 1, 2, 3. Sum of all these lengths should give you that number, right? Your breadth is 0.25 and 0.125 for one brick wide and half brick wide, which is given in the given in the problem statement. And this height is your 3.3 minus 0.85 plus your 0.125, which is your slab height. So you get the height for your exterior and your interior infill, and you assume 20% opening. So you take 0.8 factor over here to account for the 20% opening. Does that make sense? Yes? All right. So that's the sum of all the entire weight. So the total weight on each floor is this plus total seismic weight on each floor, right? Is 6115 kilonewton. So the mass of the floor is kilonewton times 1000 to convert into newtons divided by 9.8. So roughly 623,000 kilograms. Make sense? Okay, I'll let you catch up till this point. Take a short breather here. Weight of the roof similarly is 3648 divided by 2, because at the top level only half of the floor comes as a lump mass model, right? Plus the seismic weight of the roof is 4023 kilonewtons. That corresponds to 410,000 kilograms. Make sense? So you have mass of each floor, mass of roof. The next step is pretty similar to what you probably have seen before, right? So you have your mass, MI, for each floor up till 9. Roof is a little bit less. HI. What is HI?
3.3.
3.3 meters. 3.3 meters all the way through. 10-story stall, so a total of 33 meters. Which implies, which is the critical story? The ground floor. So your story 1 will be the critical story, right? Now calculate phi I for each story, as we did in the morning. Phi I is 4 by 3 HI over H. Multiply by 1 minus 0.25 HI over H. So you add that in, populate your column that way. And the check is at the roof, your phi I should be 1 because it's a relative displacement profile, right? Phi I is 1 at the roof. That means your function and your formulas are working. So your phi C is phi C is phi 1, right? Your HSC is 3.3. So calculate delta C. Theta D we know is 0.028 times 3.3 is 0.0924 meters. That's our delta C. Have your delta C, you have this equation, you have phi I, you have phi C, delta C, that can give you delta I. So delta I, if you look at the formula and where it's referencing your phi I, it's referencing delta C, which is right here with a dollar sign, and it's referencing phi C again, which is V65. Right? Just to check whether we are doing it right for every row within the column, you can check the other formula as well. You have phi C referenced, you have delta C referenced, and you have phi I as a floating variable. Make sense? You calculate delta I for all the 10 stories. And these three columns are pretty self-explanatory. Mi delta I square, mi delta I hi. Once you find phi I and delta I, your life is much more simpler. Using these formulas over here, calculate delta D ME HE. Following so far? Are you getting the same numbers? Will these numbers change for long direction and short direction? Yes? Why? Why would these numbers change for long direction and short direction? What does single degree of freedom system means in practicality? So is a single degree of freedom system dependent on direction? So why would it change? It will not change because it's a single degree of freedom system. That's the whole point. You're taking a multi-degree of freedom system, morphing it somehow into one lumped mass model, one mass lumped at the top, and 1 degree of freedom that it can move. So did everybody get this number? delta D MEHE. Okay. What will change is probably your time period in different directions. But the parameters will be the same, right? The delta D MEHE will be the same, your time period might change. So now you have to do analysis for the long direction and the short direction, right? So let's calculate theta YF is 0.5 strain times LB over HB. We have different LB and HB. So what's our LB and HB? Let's write it down. Is 5.5 and 6.5, and HB is 0.75 and 0.85. Right, and the long and the short direction. Which one is which? So your LB in the long direction is 6.5, and the short direction LBS is 5.5. Then HBS is HBS is 0.75 and 0.85 respectively. Right? 0.75, 0.85. B. Okay, now when you plug that in here, you get our theta YF, which is 0.0091 and 0.0096 in short and long direction respectively. Delta YF is your theta YF times your equivalent height. Yes or no? So your delta Y is theta YF times HE. So this times your equivalent height, which is over here, 21.87. Same over here. So roughly you're getting similar numbers, very minute differences. We are doing all this exercise to calculate what our ductility will be, which is delta D over delta Y. We know what our delta D is, which is 0.510. 0.510 divided by 0.2 is roughly 2.54. 0.510 divided by 0.209 or 0.21 is 2.44. Greater than 1. That means it's okay. Our equivalent viscous damping, 5 plus 120, 1 minus 1 over mu, under root over pi. Calculate that. You have the mu for both different directions. 19.2 in the short direction, 18.7 in the long direction. Why is the short direction has much more damping? Something to think about. So 19.2 and 18.7. Now we look at in our displacement spectra. And 0.54, that's the horizontal line we are tracing. And for different equivalent damping, we will look up the time periods. So roughly estimating with our displacement spectra for 19.2, which is roughly 20, somewhere over here, 0.54 delta D is 4.3-ish, 4.3. And similarly for 18.7, which is not much different, it's 4.25, or you can even go to 4.3. Make sense? This is always from displacement spectra. Now, once you have time period, the next step is to calculate KE. Plug that in here. Again, this is a typo. Times DE. Formulas are right, but that was a typo over there. So you have similar similar stiffnesses in either direction, with subtle differences, but not much. When you change the unit, it's much more prominent. It's 10,589 or 10,590 rounded off, was 10,840 kilonewton per meter. VB in terms of kilonewtons is KE times delta D. Delta D is from our STOF system. KE times delta D. So 5399 versus 5529 in the short and the long direction. Following so far? Next step. Divide the VB in different stories in both directions. Using VB times MI delta I over summation of MI delta I. So you have MI delta I calculated from up there in a different table we had. Phi I delta I. MI delta I, summation of MI delta I. So your VB in the short direction will be divided in stories like this. VB in the long direction will be divided in stories like that. And you can look up what you're referring to is MI delta I over the sum of MI delta I times your VB, which is right here. And a good check of that is if you sum the forces in the stories in the short direction, that should be equal to VB, 5399 versus 5399. Same 5527 versus 5527. So that tells you that you didn't go wrong anywhere in the problem set. Okay. Questions? I would probably give you one homework, which is do spend some time with the Excel sheet and clean it up so that you can use it later in the future whenever you're doing problem performance-based design. So while this is fresh in your mind, just clean up the spreadsheet so that everything is laid out as per how you want it. Any questions? So tomorrow morning, probably, Mr. Mohit will give you some